Welcome to the demonstration corner. Today we'll be demonstrating the MP-1 transient plane source method on the MP-1 for testing peak. There's a few different ways of measuring polymers depending on their dimensions. We'll talk a little bit about that. But before we do, tradition here at the demonstration corners, we do a little circle to show the equipment that we have available for demonstration and training, whether it's before sale or after sale, and this is really a critical part of what we do here at Thermtest. So let's turn the camera. This is our GHFM01 for measuring thermal resistance and thermal conductivity of complex materials. By complex, I mean heterogeneous or non-repeating layers through the thickness. So typical dimension is 2-inch diameter. The thickness height can be thin film scale up to 1 inch thick. How we define heterogeneity in terms of what we measure is whatever the added filler or layers are, how its homogeneity is in relation to the property you're measuring. So it's not quite the same as looking under a microscope. So the effect of what you're modifying the material, that could be the conductivity and the size of the filler in relation to the matrix or non-repeating layers, etc. All of those can affect other methods where resistance doesn't rely on that same assumption. When you're measuring resistance, you are forcing a delta T across the sample and looking at a one-dimensional heat travel. So to facilitate that, these two plates come together at a 20 degree, as an example, delta, and the oven comes up. It's all motor controlled. It comes up and is set at the mean temperature between the two plates. And that gives you a one-dimensional heat path that's well defined. This measures thermal resistance, and with the measured thickness of the sample from the optical encoder, you calculate thermal conductivity. The operational temperature range is from -20 to 300 Celsius. This follows ASTM E1530, E1530, and that is our GHFM01. The other steady state method, so the GHFM01 is a steady state method. The other steady state method is the heat flow meter, and this is for measuring thermal resistance of heterogeneous materials or non-repeating layers through the thickness, but it's aimed at measuring the insulation range. So the GHFM01, its conductivity range is roughly around 0.1 to 100 watts per meter Kelvin. The heat flow meter is designed for more construction and insulation materials. Its conductivity range is 0.00, approximately 2, up to 0.5 watts per meter Kelvin, and you can extend that with a high thermal conductivity kit up to 2.5 watts per meter Kelvin. It's generally used for materials that are heterogeneous and used on a macro scale that can be inserted, and the two plates come together and you get the thermal resistance and thermal conductivity. This is one size, our HFM100, that stands for the thickness. The opening is 100 millimeters thick. The sample size of this model is 300 by 300. And the other model we have is HFM50, which is 50 millimeter opening. And the other dimensions are 200 by 200 millimeter. There's one other, the plate temperature of both the HFM100 and the HFM50 are plate temperatures of -20 to 75 Celsius. The actual mean temperature range depends on the delta T that you have across your sample. We have a high temperature version of the HFM100, which is -30 to 110 Celsius. So that is our heat flow meter series. That's one model of it. Typically, we would have a TPS 2 here. That's being used in another part of the lab. Otherwise, that would be our, you can see that information from our other demonstration videos or on the website. That would be our transient plane source standalone instrument following ISO 22007-2 for measuring bulk conductivity, thermal diffusivity, and volumetric specific heat. There are other modules you can add to it for thin films, anisotropic, slab, etc. You can add other temperature options to it. It has two conductivity range, up 0.01 up to 100 watts per meter Kelvin and 0.01 up to 500 watts per meter Kelvin. This is our transient hot wire for measuring thermal conductivity, thermal diffusivity, and specific heat following ASTM 7896. It is designed for liquids and phase change materials. Its temperature range, it has integrated temperature control. It's a proprietary temperature platform that's integrated into the unit. This unit as it stands is 10 degrees to 200, but it can be packaged depending on your needs from minus 160 up to 300 Celsius. So there's different temperature ranges. The sensor is designed specifically to limit the effects of convection, which is the enemy when you're measuring fluids. To also be able to measure a wide viscosity range and test past boiling points, you can back pressure the sensor up to 20 bar and 35 bar. So that's the Transient hot wire. The baby brother to the heat flow meter series is our HFM 25, and this is designed for measuring small format insulation materials from 2 millimeters up to 25 millimeters thick. The sample size can be as small as 2-inch square. So that's customers were asking for the ability to measure smaller samples, R&D size scale samples with the heat flow meter method. And down the other end is the baby brother to the MP-1, which is our MP-2, which has primary sensors for measuring solids, liquids, so transient plane source, transient hot wire, and transient line source. They have more narrow ranges, but the unit is quite accurate and economical. So, coming back to the MP-1, this, if you recall the discussions around the THW and the TPS method, we brought those two together to form our marquee transient method. So this is the marquee transient instrument on the market due to several characteristics that it has. Every MP-1 can be acquired with just a controller. I separate that to show you that this is a standalone controller. Every MP-1 has a 4-channel switch built in, so it's a 1 channel in the front and 3 channels in the back, and that gives you the ability to measure one sample at room temperature or multiple samples at room temperature by any of the methods that are available on the MP-1. It also allows you to add temperature platforms. Again, this works off of our temperature platform, proprietary heating and cooling for the transient plane source and the transient hot wire. The transient plane source temperature platform as it is configured here is 0 degrees to 300 Celsius. There's no external cooling needed. That's all built into the unit itself. The transient hot wire platform as it sits here is 10 to 200. Again, both of these can be configured to minus 160 to 300 Celsius. So it just depends on your requirements whether or not you need that lower temperature range extended. So these both methods, transient hot wire and transient plane source, the temperature platforms and room temperature sensors can all be operated from the same controller, and the software is smart enough to be able to schedule all those different channels to take advantage of the capacity it has. So essentially the MP-1 is like having 4 controllers side by side with the ability to measure everything and control everything smartly. Some of the other things that make the MP-1 unique in the market is when you're measuring high conductivity, the MP-1 has a conductivity range of 0.005 up to 2000 watts per Kelvin. What facilitates that is its ability to record small test times in our data collection, our frequency of data collection. So this shortest test time available in MP-1 is 0.25 seconds, where we're actually collecting 600 data points. So with that many data points, we can cut 0.25 seconds down to a much shorter window. So when you're looking at transient methods for measuring solids, like the transient plane source method, one of the key principles is the ability to vary time. One of the assumptions of a measurement is that your heat that you're introducing into semi-infinite body is staying within the dimensions of the sample. That is physics. That is one of the assumptions of the method. If you're hitting boundaries of your sample, you are going to get effects of reflections and disturbing your raw data, and your data will be wrong. You'll be breaking one of the assumptions. So test time is really critical. So the more conductive your sample is, the smaller it is, the more important it is that you have a variety of times to be able to stay within those dimensions. So that large conductivity range, such as graphite sheets, which have a very high thermal diffusivity, are part of what makes the MP-1 unique in terms of transient methods. And there's a whole bunch of other features that make it unique, but those stand out as the highest priority. So today, we're going to talk a little bit about peak in terms of different configurations of that material and how it can be measured. This is just some standard pieces of peak that are roughly half-inch stick or 12.8 millimeter stick, and a radius of 10.5 or 21 millimeters diameter. So we'll be showing you a short demonstration on that in a moment, but of course PEEK comes in different sizes. These have already been to temperature many times. We've measured these with the guarded heat flow meter. That's why they are 2-inch diameter and have this sort of color to them. They've been up to 300 degrees many times. Sheets of PEEK in different thicknesses. These can be measured by the transient plane source slab method, and so can these. So these are roughly a few millimeters thick. These are roughly around 0.3 millimeters thick. We're able to measure this with the TPS slab method with the backing correction that's available on the MP-1. That's again a proprietary extension of the slab method to be able to measure lower conductivity thin polymers with the slab method. So those two can be used on the slab method. Again, looking at configuration and dimensions of sample to extend the method. The other option for measuring very thin materials is our thin film module. So this is essentially the same thin film, a little thinner, 0.25 millimeters thick. We can measure the intrinsic properties of that with our thermal resistance thin film method that's available on the MP-1. So this method allows you to measure 1, 2, and 3 layers and draw a straight line through the change in thermal resistance. Again, this is a method of measuring thermal resistance with a transient method, so it's very unique. So we can measure the 1, 2, and 3 layers of thermal resistance and plot that, and the slope, the inverse of the slope, so 1 over the slope, is the thermal conductivity minus the effects of contact resistance between the samples. So that's an important way of determining the intrinsic properties of thin materials. So that can be used to measure a very wide range of thickness because it has this ability to layer out. And that multi-layer approach is the same that's on the other thermal resistance methods that are on the market. ASTM E1530 and ASTM 5470 for electronic dielectric electronic materials. Both of those describe multi-layer approach to backing out thin film. So we're using a proprietary transient method of measuring thermal resistance, but very specifically we're measuring resistance, which gives us the ability to back out the intrinsic properties. So those are a few descriptions of the approaches to PEEK. I guess the only other approach to PEEK would be if you want it to measure through the melt. So we have a very specific cell for measuring polymers through the melt, and it is very clean. It's still using the transient plane source method. It's very clean. It doesn't destroy the sensor, and we've made those measurements of PEEK, of course, up to 400 degrees. You can find information on the melt cell option on our TPS. Of course, we will eventually have a demonstration on the melt cell as well. So we've been doing polymers through the melt for quite a long time. So I'm going to go to the desktop and walk through entering the dimensions of the sample. We're going to show you how the ITPS works. So that again, with all of our transient methods, we've added the intelligent transient element, which is the ability to automate all parameter selection with just inputting the dimensions of your sample. Of course, we're following the ideal theory, and you always have the ability to analyze raw data as an expert, but both levels of user experience we include. So I'm going to go to the desktop. You should see this is our opening screen. Our software is separated out into 2 sections. So this is data acquisition, which controls all the it controls all of the items that are connected to the controller. So here you can see a number of items. You have the controller itself, and it has 4 ports. We actually have all 4 ports populated with a device. So here's our TPS transient plane source, transient hot wire plane source, and 2 sample holders that are sitting on the bench. You could see those in the previous video feed. So each of these devices auto-detect and sort of stay connected throughout. So you can schedule all these different channels and be able to maintain a volume of testing. And then the analysis is a separate application that lets us review the raw data and calculate. We put those into 2 separate applications, and that was really important user experience element for us, because if you try to compile it all into one, there's a lot going on. So this gives us a lot more power to take advantage of the the multi-channel and schedule measurements in a nice, convenient way. So, user, these are some of the elements you can add to the measurement. So we're doing symmetric. We're going to do a two-sided measurement, isotropic. This sample is defined as semi-infinite, so it's a bulk measurement. The measurement device itself is auto-detecting. We're going to run room temperature. We're not going to run the temperature platform. We have other demonstration videos on that, but also you can select the other temperature platform for the transient hot wire if you were going to do liquids. So you would name your sample. You would put in the height of the sample and the radius, which is 10.5 millimeters. And we're going to select the port that we're going to make the measurements on. And I'm going to ask the software by clicking this button, which sensor size should I use? So this is 2117, which is a radius of 3.2 millimeters. So before I go any further, I'm actually going to, I'm sorry, it's port 2. Yeah, port 1 is we're doing some thin film measurements. So port 2 is the other sample holder. I'm going to share the other camera. So now that we know the diameter, we're going to set up the sensor in the sample, and then we'll come back and check the resistance. As of right now, there's no sensor connected. So you should see this is the second sample holder that's connected into port 2. I think actually it's port 4. Yeah, that's the room temperature. Otherwise, it's the temperature platform. So they're labeled correctly. It's just me not paying attention. So port 4. So let's go to that camera and set up. So this is sensor 21171. This is our peak samples. Here's our 4 contacts that are common for the transient plane source sensor. So we're going to insert those into the adapter, the MP-1 adapter. And that just lets us, there's a window in the back that tells you when to stop. And we just turn that down and we have a setup sensor. So all of our sensors are configured this way. You can purchase a sensor with a permanent cable, but it has no advantage. The advantage of this is it makes the sensors less expensive and more durable. You can upgrade this cable. As of right now, the room temperature setup, this one, is good to up to 80 C if you wanted to put this in your own chamber. But if you wanted to extend the range of this sample holder to 300 Celsius, we offer a 300 degrees Celsius adapter that lets you use essentially everything except a different adapter. So we can change the height of the sensor by moving it up and down. So we're going to do a symmetric test. So we're going to put one sample piece on the bottom and one sample piece on top. So that's our configuration. We're going to introduce just a plate so that we're not scarring our sample. And then we're going to lower the top plate till it's approximately in the right location, and then just on a smaller scale, just tighten it there. That's it. That's your complete configuration of sensor to sample. So now we can go back to the software. So here's our software. So let's check the sensor, make sure that we have good electrical contact. So this verifies the electrical resistance. It's good. The temperature is taken from the adapter itself. It has a PT sensor integrated into the adapter. If you were using one of the temperature platforms, it'd be identical. You'd be drawing the temperature from the actual device itself. So our ITPS is where we get our thermal conductivity parameters, so test time and power. So by selecting the range of material conductivity, basically it automatically develops the parameters from that. Now it doesn't just take them from a database of random powers and times, but what it does do is a continuous measurement. So by clicking this, it's going to make a continuous measurement, and it already knows the height of the sample and the radius. So what we're looking for with our parameters of power, we're looking for a nice clean signal free of noise, and from our test time we're looking to stay within the dimensions of the sample. Additionally, and if you purchase an instrument, this is part of the training, we manually teach you how to select these parameters as well, but the ITPS does that for you. The additional element that time is doing is penetrating deep enough into the sample so that you are getting a bulk shape of penetration. So this is using the three-dimensional module or method. So if you're following the ISO properly, you want to penetrate at least a radius of dimension into the sample in all directions. So from the edge of the sensor to the edge of the sample, we want to penetrate at least the radius of the sensor you're using. So picture like a half-sphere shape. We want to make sure all directions are at least the radius. So the ITPS is defining what are the outer boundaries of the sample with time, and then what time can we select with what's available in the outer boundary to satisfy what is really called the total to characteristic time. So this is doing all that for you. So it is balancing the bridge right now. It will make a continuous measurement too short to the length of too long. And that little gap that's in between the too short period and the different lengths of time is the delay when the instrument is feeding the data to the analysis application for calculating what the diffusivity is and what the properties are at that time. So it'll extend out and measure past the boundaries on purpose to define the time that has the boundary, and then it'll select power and time based off of the available dimensions and the thermal diffusivity of the material, and recommend those to the user so that they can select those. So we're following all the idea theory with this. That's really a critical part. We want to be really open about that this is not calibration. We're not correcting anything. We're producing the user that iterative approach that a manual approach would be. So we're doing that automatically with this intelligent software element. So we can watch this for a bit, and once it's done, we'll go to the next window with those parameters that it's asking us to use and schedule a measurement. Then we can review some data that I've previously measured on the same sample. So if you were to select the wrong conductivity out of that grouping, it will automatically change to a different conductivity range. So if I were to select below, if I don't know what the conductivity range of this is, if I were to select the very low conductivity, it would know that based off the power range that's available on that particular category, it would automatically know that you haven't achieved it. So it would actually move to the next category automatically. So it's done. It wants us to do 40 seconds with 9 milliwatts based off the dimensions of that sample. And we can hit close, and I can go to the next window, and we'll just garbage those, and we'll start a measurement of 5 measurements, 10-minute delay at 40 seconds. And we don't have to be as specific about the power, but we could. And there's a 10-minute delay before the first measurement, and by clicking start, it's automatically scheduling that measurement to happen in 10 minutes from now, and it'll repeat each measurement until it's complete, and this event log will show all the different stages. So here you have that 10-minute stabilization. So if we go to the data, we can see our peak and the results of this peak for thermal conductivity, thermal diffusivity, and volumetric specific heat, and the average data for it. That's it. So basically the conductivity of that material is around 0.29 watts per Kelvin, and the volumetric specific heat is around 1.38, and that's at a temperature of roughly 23 or 24 degrees. So that concludes the demonstration and a description on how to measure different dimensions of a PEEK or a polymer type material with the capabilities of the MP-1. Some of these capabilities are on the TPS-2 as well, so obviously you're able to measure these types of materials with the TPS-2. Just the MP-1 gives you quite a bit more punch depending on temperature range and some of the complexities that the sample can have. That concludes the demonstration. If you guys have any questions, please get in touch with us. We're happy to answer that you have. Thanks for joining.